All right, so last time we talked about angle of twist in beams with torsion, internal torques, and we had this formula for it. The angle of twist is equal to the torque times the length divided by G IP. And then we had the two other forms. One was the sum formula. If these values aren't all constant along the length of the rod. So the torque on the ith piece times the length of the ith piece divided by G for the ith piece, I sub P for the ith piece. And then if any of these are varying continuously, you have the integral formula. The torque is a function of x over G as a function of x, I sub P is a function of x, and you're integrating all that with respect to x. And we did one example problem. So now let's see how this works in a statically indeterminate system. So a statically indeterminate, that's not how you spell that. Indeterminate torsion member. Okay, so let's say that we have this member that's fixed on the left and fixed on the right. And in the middle, there's a torque applied of 5,000 Newton meters. It's a circular cross-section. With an area equal to 0.01 meters squared. And Young's modulus is 200 times 10 to the 9th, and the Poisson's ratio is 0.25. The whole thing is half a meter long, and this is happening at the midpoint. And we want to know what are the reactions. Okay, so first of all, what that torque in the middle, what's that doing? Describe what's happening there. Think about what's happening there. So yeah, that's so it's going this way. So there's something here, like you could imagine, like a wrench or something connected to that. This is connected to some kind of big motor, and it's turning it like this. So the middle's getting twisted, but the two ends can't go anywhere because those are fixed. And so the total angle of twist is equal to 0. Okay? In between the two endpoints, it can twist. But if you add up the total angle of twist from the left to the right, it has to be equal to 0. So how do we know it's statically indeterminate? Well, first we just have to do the statics and see what we have. So we have this applied external torque of 5,000 Newton meters. And then over here, I'll call this torque at B, and I'll call this the torque at A. We can leave off any other reactions because there's nothing going on except couples in the x direction. Here's the orientation I'm going to use. And so the rotational equation about x says TA plus positive 5,000 plus TB is equal to 0. So we get our first useful equation that says TA plus TB is equal to negative 5,000. That's one equation for two variables, so we can't solve it. So now we have to look to the deformation to come up with another equation. Okay, so now the angle of twist. To do that, we have to cut this because the internal torque is going to be different on the first half than it is on the second half. Yeah, half a meter. So cut 1 is valid for the first half of that member, so 0 to 0.25. We have the external torque, the reaction torque of TA, and then we have an internal torque of T. That's what we're trying to find. And so the moment equation about the x-axis says TA plus T is equal to 0. So the internal torque is equal to negative TA. Now we can use this to find the angle of twist on the first half. So the angle of twist 1 is equal to the torque times the length divided by g IP. The internal torque is negative TA. The length is 0.25. G and IP, we haven't calculated those yet. I think maybe those are going to cancel out. Let's just leave those in there for now, and those are going to cancel out in the end. And now we can go on to the second cut. For x values between 0.25 and 0.5. So we have the torque at A. Now we've gone far enough to the right that we also have that applied external torque of 5,000. And then we have the internal torque. And the moment equation about the x-axis says TA plus 5,000 plus the internal torque is equal to 0. So the internal torque is equal to negative TA minus 5,000. Okay, and then the angle of twist for the second part is equal to the internal torque times the length divided by G times IP. The internal torque is negative, this should say A, yep. So we have negative TA minus 5,000. that quantity times the length of this second piece, which is 0.25, divided by G times IP. And so now we can combine those two pieces. The total angle of twist is equal to the angle of twist, the angle of twist for piece 1 plus the angle of twist for piece 2, and those have to add up to 0. So our first one said negative TA, so negative TA times 0.25 divided by G times IP, plus our second one, negative TA minus 5,000 times 0.25 divided by G times IP is equal to 0. You can multiply both sides by G times IP. And now you can divide both sides by 0.25. And you end up with the second useful equation, which says negative TA minus TA minus 5,000 is equal to 0. So 2TA is equal to negative 5,000. So TA is equal to negative 2,500. So now we have a system of two equations for two variables. The two reaction torques have to add up to negative 5,000. So equation 1 says TB is also equal to negative 2,500. B, thank you.
Is that because the torque was applied at the center of the beam, not somewhere else? Just because of the length?
That's right. So if that torque was applied closer to point A, then the first half, then the reaction at A would be bigger. Yep. Okay, so now that says that from the start to the end, the total angle of twist is 0. What's the angle of twist on the first half of that beam? So what's the angle of twist from A to the middle?
Do we have to find the IP now?
Yeah. Mm-hmm. So the angle of twist is equal to the torque times the length divided by G times IP. And we know that the internal torque is negative TA. So that's negative of negative 2,500, so positive 2,500 times L, and that L is half of the length of the beam, so 0.25, divided by G times IP. And G is equal to E over the quantity 2 times 1 plus nu. So that's 200 times 10 to the 9 divided by 2.5. So what do you get for G?
8E10.
Okay.
Is that a unitless thing?
No, G is a modulus of elasticity, so that's pascals. Because E has units of pascals and nu is unitless. And then the polar moment of inertia, let's see, that is, I think that's pi over 2 to the 4th, is that right? Pi over 2 times the radius to the 4th. So that's pi over 2 times 0.01 to the 4th.
That's the area you gave us.
What do you mean radius? You gave area as 0.01.
Meter squared.
Oh, I gave, that should have said radius. So that should be the radius is equal to 0.01 meters. Sorry about that. Thanks. Okay.
Which was it?
This time.
Yeah, better not do that now.
Okay, so what do you get for that? 2.
1.571 times the negative 8.
Yes. And that has units of meters to the 4th. So the angle of twist is equal to 2,500 times 0.25 divided by 8 times 10 to the 10th times 1.571 times 10 to the minus 8. And what do you get for that?
0.497.
0.497 radians.
How do we get radians? If you're talking about
Units, let's see, so we have, this is Newton meters.
Okay.
This is meters. So let's write it out. So Newton meters times meters divided by pascals. So this is
Newton's
per meter squared. And then this is meters to the 4th. And so you get newtons cancel, all the meters cancel, and you get a unitless thing, which in this case is radians.
28 degrees.
Okay, 28 degrees, that's a lot. You might not want to do that to a steel bar and count on it much after. But that's how the calculation goes. Okay, so that's positive, so that's in the, so that twist is in the, coming this way, in the positive x direction.
What was the angle like when you twist the bar or try to bend it? That there's like a point where there's no return for the bar to go back to its original form.
The buckling,
Something like that. I know we went through that like earlier in the semester.
What was the graph?
It was kind of a graph.
You had, it was like linear and then it
Oh, so yeah, that was just the stress strain curve, and it's just after it leaves the elastic region, then you get into permanent deformation. And materials are still strong for a while when they're in permanent deformation, but eventually you get to a point where they're weakened.
Does that graph also can be used for the angle of twist?
That's stress versus strain. So you could do a graph like that for shear stress versus shear strain. I can't picture, maybe I've seen that graph before, but I can't picture what it looks like. I don't know if it has a similar characteristic. Okay, so what would be, what's the angle of twist for the second half? Yep, exactly. Since we know the two of those angle of twists have to add up to 0, this one has to be equal to negative 0.497.
Does that also hold when your twist is off the center? Your angles should also add up to 0?
If you're
putting torque not in the middle, but
yeah, so if the bar is fixed on the two ends, then no matter what loads are applied, they have to add up to 0 twist.
no matter what location.
Yeah,
Okay.
because that's just a property. That's just saying that they're fixed in a way that you can't move them. You can move the stuff between them, but you can't move those 2 points. Okay, so let's do an example where we use elongation and angle of twist. So let's put the loads not at the midpoint, but halfway between the midpoint at the end. So say that's 1 meter long. And then these loads are going to be applied 1/4 of a meter from the wall. So let's have a torque of 1,000 Newton meters. And let's have a tension of 4,000 newtons, or an external horizontal load. And then let's say that the temperature is increased 50 degrees Celsius from the equilibrium temperature. The temperature where if you took all the loads off, there'd be no loads on the walls.
Maybe you could say the temp that they built the structure.
Yeah, right. Right. Yeah, this probably isn't the best way to say it, but yes, from 0 load temperature. What are the reaction loads? Okay, so we're going to start out by doing the statics, and then we'll see where we're at and think about where we're going to get the extra equations. Free body diagram. We have the external loads, so we have 4,000 there, and then we have a couple of 1,000 at the same point. And then the reactions here, we have a horizontal force. I'll call that RA. And we also have a reaction torque. I'll call that fancy TA. And then on the other side, we have the horizontal reaction RB and the couple fancy TB. So Newton's second law, we're only looking at the x components. That says RA plus 4,000 plus RB is equal to 0. So our first useful equation says RA plus RB is equal to negative 4,000. And then the moment equation about the x-axis says fancy TA plus 1,000 plus fancy TB is equal to 0. So our second useful equation says torque A plus torque B is equal to negative 1,000. So we have two equations for 4 variables. So we're going to need 2 constraint equations. Okay, so one of those equations is going to come from requiring that the elongation over the whole length of the beam is equal to 0, because it can't grow at all when it's fixed between the two walls. And then the other one says that the angle of twist, if you go over the whole beam, has to be equal to 0, because neither of those 2 points on the walls can rotate. Okay. So let's do elongation first. We're going to have to do that in 2 different steps, because we have an elongation due to the forces that are applied, and we have an elongation due to the change in temperature. So our main equation says that the total elongation, which is equal to the elongation due to tension plus the elongation due to the temperature change, has to be equal to 0. So the one due to tension let's see. So for this one, we're going to have to do 2 cuts, because the internal tension is going to be different on the left quarter of the beam than it is on the right 3/4 of the beam. So cut 1 is valid for x's between 0 and 0.25. Did I give any information about this? Yeah, we do need alpha. So alpha is equal to 5.0 times 10 to the minus 6, 1 over degrees Celsius. And then the other ones, I think we're going to need those too. So let's say Young's modulus is equal to 100 times 10 to the 9th pascals. Poisson's ratio is equal to 0.3. And the radius is 0.01 meters. Okay, so cut 1. We have the force RA, and we have the couple fancy TA. And then this is before we get to the external loads. So the only other loads on this are an internal tension and an internal torque. So Newton's second law, X component, says RA plus T is equal to 0, so T is equal to negative RA. And then the moment, what? Yeah. The moment equation about the x-axis says torque A plus T is equal to 0, so the internal torque is equal to negative torque at A. We're only dealing with elongation right now, but we'll come back to that later. And then cut 2 is valid for x's between 0.25 and 1. So on this one, the loads are RA and the torque at A. And then a quarter of the way in, we have, was this the direction of the force? Yeah. So we have a horizontal force of 4,000 newtons. And a horizontal torque of 1,000 newtons. And then we have the internal loads, T and fancy T. So Newton's second law, X component, says RA plus 4,000 plus T is equal to 0. So T is equal to negative RA minus 4,000. And the moment equation says torque A plus 1,000 plus the internal torque is equal to 0. So the internal torque is equal to negative TA minus 1,000. Okay, so right now we're doing the elongation. So the elongation due to the external forces for piece 1 is TL over EA. For piece 1, that internal tension is equal to negative RA, and the length is 0.25. The Young's modulus is 100 times 10 to the 9. And the cross-sectional area is pi times 0.01 squared. Can someone calculate the denominator there? So you get negative 0.25 RA over pi times 10 to the 7th?
Yeah.
Okay, and then for the second piece, delta 2 is equal to this expression for the internal tension. So negative RA minus 4,000. And what's the length of that piece? 0.75, yep. Divided by the same denominator, so pi times 10 to the 7th. And now you can put those together, and the elongation due to tension is equal to negative 0.25 RA over pi times 10 to the 7th plus the quantity negative RA minus 4,000 times 0.75 divided by pi times 10 to the 7th. So that's the elongation due to the internal tension, and now we have to figure out the elongation due to the change in temperature. So delta due to the temperature change is equal to the coefficient of thermal expansion times the length times the change in temperature. So that's 5 times 10 to the minus 6 times the full length of the beam, 1, times the change in temperature, 50. And so you get 2.5 times 10 to the minus 4.
Question for you.
Mm-hmm.
I know, like, from experience, I know that when something, let's say the bar is twisting or put some force on it, it starts to heat up in some way. Like, I know that the change in temperature shouldn't be that great, but should we take into account that temperature?
You know, as long as it's in its elastic range, that shouldn't happen. I think what you're talking about is once it goes into its plastic range, then it starts to convert. When it's still in its elastic range, it hasn't converted anything to heat because when you unload it, it gains all that energy back. Okay, so yeah, you're talking about bigger deformations, and we're not talking about those in this class. But like with a paper clip or something, we're not talking about that. We're talking about, imagine such a small amount of deformation on a paper clip that when you let go of it, it went right back to its original shape. And so now we can put these all together. The total elongation is equal to negative 0.25 RA over pi times 10 to the 7th plus 0.75 times the quantity negative RA minus 4,000.
The tension is just negative RA minus 3,000 over pi.
Okay, I'll just multiply all this stuff through in a second. The denominator pi times 10 to the 7th. And then the elongation due to the temperature change is 2.5 times 10 to the minus 4th. And all of that stuff has to be equal to 0. So what do you get if you multiply 2.5 times 10 to the minus 4 times pi times 10 to the 7th? 7,000.
7853.98.
Okay. And let's see, over here we have negative, so minus 0.25 RA, minus 0.75 RA, so that's just minus RA, minus 3,000. And so RA,
Shouldn't the 7,000 be negative?
yes, you're right. So RA is equal to 4,853.98. And then RB, we have equation 1, so we can solve for RB. They have to add up to negative 4,000. So what's that? Negative, RB has to be negative 8,853.98.
What are the units again?
These are forces, so those are newtons. And then the torque, the angle of twist, we have the angle of twist on piece 1 is equal to, let's see, we calculated the internal torque here. So the internal torque on the first piece is negative TA. The length is 0.25. I think we can just write this as G and IP. And so we just get negative 0.25 fancy TA divided by G times IP. For piece 2, our internal torque is this thing, negative TA minus 1,000. The length of that piece is 0.75 divided by G times IP. And the total angle of twist is phi1 plus phi2, and that has to be equal to 0. So negative TA times 0.25 divided by GIP plus the quantity negative TA minus 1,000 times 0.75 divided by GIP is equal to 0. You can multiply both sides by the denominator. And you get negative TA times 0.25 plus negative TA times 0.75 minus 750 is equal to 0. And so fancy TA is equal to negative 750. And then you can go back to the second static equation that we got. TA plus TB is equal to negative 1,000. So fancy TB has to be equal to negative 250. Any questions about that?
So that'd be useful, you know what kind of forces you're going to apply to something, then you know the limits of the buckles or something, or whatever's fastening it to the...
Well, you could use it for something like this. If you, we haven't done deflection yet, so, but this is the basic idea. Like, if you had a beam that was cantilevered at the end, and then also supported by a roller at the other end, that's statically indeterminate because, okay, and you're applying some force here and some torque here. Okay, that's statically indeterminate because this thing would stand up just fine according to statics without that roller there, so it's redundant. But if we take the deformation into account, we can figure out how the load is distributed between the couple that can be provided by that cantilever and the force here to support this, so that you know that the height has to be its original height here. You know, because of the roller, the height has to be its original height here. And so that's the kind of problem you can do. There are just a lot of cases where your joints aren't restricting the degrees of freedom, the minimum that they could be. And for statics, that's what you need. You need, in order to solve it by statics, you need your joints to be providing exactly the amount of constraint that's required. Sometimes with that kind of stuff, you pretend that the joints are something else. Like, when we talk about trusses, everything's connected by pin joints. If you look at a real truss, you see something like this at the joints. That's not a pin joint. This doesn't allow free rotation of those members. But since the forces that this joint provides to the members dominate the couples that's capable of providing, people, when they do this mathematically, they simplify this by pretending that it's really this. And you can get good results that way. But if those couples were providing important, restrictions on the motion, then you'd have to use statically indeterminate approaches.
So is there a reason that the left, that what we actually see in reality is used over a pin joint? Is it just like a cost of materials thing?
Yeah, I think it's a cost of materials thing. Yeah. They just take these two big plates. I mean, if this is a bridge, they just take these two big plates and put them in and rivet them in, like putting together a system with actual pins, and there's no benefit to it, and at least to my mind it seems harder to make. I don't know that that's true, but that's what I would guess.
Would they just literally nail a plate on if it was just?
Uh-huh. Yeah.
Just a nail plate and
Yeah, right.
one hit and that's it.
Right. It's just easier. That's what I think. Okay, have a good weekend.
Are you going to post